Welcome to our channel of Sciences and Mathematics. Our topic for discussion for today is going to be the concept of Charles' law, and this is part of the relationship that exists between temperature, pressure, and volume. And in one of our discussions that we have talked about the concept of Boyle's law, we talked about the concept of holding the temperature, pressure, and we tried to look at the variation between pressure and volume. Now for today, we're going to look at the concept of trying to hold the pressure constant and trying to see the relationship between volume and temperature. And that's, of course, going to give us the definition for Charles' law. And from this particular example that we're going to give on the board, we're going to see the relationship that exists between temperature and volume whenever we keep pressure constant. So thank you and welcome. So for today, we're going to discuss about the concept of Charles' law. And Charles' law is one of the laws that are applicable in the gas laws that we have mentioned, one of them in our videos about the Boyle's law. But for Charles' law, it's going to give us a relationship between temperature and volume, whereby pressure is kept constant. Now, suppose we have an illustration. I'm just giving an hypothetical illustration for this. Suppose we have setup 1 and 2, whereby the first one is being subjected to a pressure of 1 atmosphere, which basically is a constant with setup number 2, which is being applied with a pressure of 1 atmosphere. Or maybe there is a transition between this, and the activity that is being carried out is increasing the temperature in setup 1. So if we increase the temperature in setup 1, we're going to see that the mass of a gas that is inside this container, the volume of that gas is going to, of course, increase. And this kind of increase is going to be proportional as to the increase in temperature. So in this case, this is a situation whereby the pressure is kept constant, and we're going to see that if this is for a decrease, this is for a decrease in volume. If we try to decrease the temperature of this specific setup for A, we're going to see that there's a decrease in volume when the two are subjected to a constant pressure of 1 atmosphere. Now suppose there's a setup number 2 whereby we increase the temperature in this specific setup of the gas molecules that are inside here. These gas molecules are going to vibrate vigorously. Of course, from the kinetic theory, we are going to see that there's going to be an increase in the vibrations, and it's going to expand, of course, and the volume inside that container is going to expand in that respect. So therefore, the relationship that exists between increase and decrease in volume, insofar as the volume and temperature are concerned at constant pressure, is what we refer to as the concept of Charles' law. So we can be able to explain this, that when the temperature of a given mass of a gas is decreased, the volume of a gas decreases as well, while the pressure is kept constant. Now we've of course talked about the concept of kinetic energy of the molecules which are inside here, which continue to vibrate at a high speed, maybe or at a high energy, when they are subjected to increase in temperature. So this proportional relationship that exists between those two aspects is what we call the concept of Charles' law, and it states that the volume of a fixed mass of a gas increases in the same proportion as the absolute temperature, and pressure is kept constant. So I've mentioned about the concept of absolute temperature, and we said in our units definition, or maybe the standard units, the SI units we are talking about, absolute temperature is measured in units that are known as the Kelvin. And we had given a relationship between, of course, or if necessary, we're going to mention this, a relationship between the Kelvin scale, and which is absolute, of course, as we have said, and there's a degrees Celsius scale and the Fahrenheit that we're going to see. But the variation between the Kelvin and the degrees scale, a change in 1 Kelvin, which is given as T, we're going to use T to represent Kelvin. So a change in 1 Kelvin is equivalent to a change in degrees centigrade, but of course there is a difference with the Fahrenheit scale, which we are going to mention later. So whenever I mention a change in temperature, for the absolute value I'm referring to kelvins, where a change in temperature for 1 Kelvin is simply going to imply the same magnitude of change for degrees centigrade. So therefore, in this case, we're going to use the concept of absolute scale, which is in kelvins. So therefore, Charles' law implies that the volume of a fixed mass of a gas is directly proportional to its absolute temperature. So I was just mentioning that concept of absolute for the case of emphasis. And therefore, this can be mathematically represented as volume is directly proportional to temperature at a constant pressure. So therefore, just like the Boyle's law that we had represented, we can be able to represent this one as V over T is equals constant. So therefore, the relationship as we had demonstrated earlier can as well be given as the change in volume to a different volume can be represented using that specific proportionality for V1 over T1 is equals V2 over T2. Now, Charles' law can be graphically represented using that absolute scale that I've mentioned, whereby we have the graph of volume against temperature. So we have those two variables. I'm going to use a small one for the sake of space. So we have that variation in volume against temperature. And we say that there's a direct relationship. So therefore, this is going to be represented as that. But basically, I've given that dotted line for that. Now, at this specific point from the 0 mark, we have negative 273 kelvins. And then we have at this specific point 273 kelvins, that is representing maybe 0 degrees Celsius on the Celsius scale. But of course, we said we're going to reserve that relationship for another discussion. So from this graph, where we can be able to interpret the relationship between the volume and temperature from the graph, which is giving a direct relationship. So this basically shows that a fixed mass of a gas expands and contracts using this specific scale. So this is a fraction of a contraction of a gas in terms of volume at 0 degrees centigrade. So whenever we are talking about 0 degrees centigrade, then therefore so this relationship, I'm going to just use figures in order to represent it. But basically this implies that if the gas is at negative 1 degrees centigrade, then therefore this is going to be 272 centimeter cubed of a gas. So I'm just going to use an illustration for an example to represent that one, so that is understood. So just going to leave this one for this. But this scale that we have indicated at this particular point, I've given a dotted line there. And when we try to look at another maybe a form of a substance, we talked about the 3 states of matter: solids, liquids, and gases. When we decrease temperature, we of course, if it's this is a solid, we increase temperature, we get a liquid. We increase temperature, it becomes gaseous. So in this case, if we try to do the reverse, we're going to obtain this one. Now, at this specific point, I'm giving a reason as to why I've given this dotted line. This point is not practically achievable. It is referred to as absolute zero, which is negative 273, of course, on this Kelvin scale. And this implies that the volume will be zero if we try to look at the variation of volume and temperature. At this point, it implies that the volume of this specific gas will be zero. Now, in reality, this is not possible because the gas will have become solid, and therefore, Charles' law will just apply as the at this specific temperature. So we are not going to consider that one for now. We just reserve it for another. Okay, so we are just going to confine ourselves from this, but I've just given the definition for this at particular point in the Kelvin scale. It's known as absolute zero. Just come in this order. So it's absolute zero at this specific point. But we've said that this law cannot be able to be applicable at this point because it's the gas will have become solid and practically not possible, but it's a theoretical value that we are referring to as absolute zero. So we're going to have an example of one of the applications of this specific law, that's Charles' law, and try to see how we can be able to find other aspects given specific conditions for temperature and volume. So I'm going to read the question, we extract the information and try to apply the concept of Charles' law and try to find out whether we can be able to find an answer for that. So it reads, so this is a sample question, and we're trying to look at the relationship between volume and temperature as application of Charles' law. A gas occupies 450 centimeter cube at 27 degrees centigrade. What volume will it occupy at 177 degrees centigrade if the pressure is kept constant? So basically this application of Charles' law, and I'm going to write the information that I've read. So maybe to repeat it again for understanding, it says a gas occupies 450 centimeter cubed. So that is going to give us volume 1 at 27 degrees centigrade, that is temperature 1. What volume? We are being asked to find V2. Will it occupy at 177 degrees centigrade? Now this is T2 if its pressure is kept constant. Now from this case, of course, we can see that this is Charles' law whereby we have a relationship of V1 T1 is equals V2 T2. We're going to make V2 the subject of the formula, and then we're going to see that it's being given as V1 T2 all over T1. So in trying to do a substitution for those specific entries, so I said for the temperature we have been given in the Kelvin scale. So therefore, I mean in the Celsius scale, we have to convert them to the absolute scale as per the requirements of the Charles' law. So we're going to add 273 plus 273 in order for us to get the temperatures and the Kelvin scale, and that is going to give us for the first one, that is 300 kelvins, and this is 450 kelvins. So doing a substitution for that for volume 2, that is T2, it's going to be 450. So that is 450 centimeter cubed. Let me see, is this one 450? Yeah. So therefore we do a substitution for that, and this is going to give us V2, as we can work out and try to confirm the answer whether it is correct, but it's going to give us that. So of essence, first remember to convert this one as per the definition of Charles' law, and then apply the formula from the information that have been given to do a substitution in order for us to find that one. So that's how we can be able to apply the second law of gases that we have mentioned apart from the Boyle's law, and that is the Charles' law that gives a relationship between volume and temperature. So that is for today, guys. Bye. God bless.